This presentation will explain how geologists figure out the conditions responsible for turning hot magma into solid rocks, and how we can make some simple observations to identify and classify some common igneous rock types.
There are three specific things we want you to learn. The first is to figure out if a rock formed near Earth's surface or deep underground. Next, we want you to further classify these rocks on the basis of their chemical composition. And finally, we would like you to be able to name some common types of igneous rocks.
We can divide all igneous rocks into two groups. Volcanic igneous rocks form on or near Earth's surface. An example would be a lava flow. In contrast, when magma cools and solidifies below ground, it forms a plutonic igneous rock.
Both volcanic and plutonic igneous rocks form when magma solidifies. The big difference is in how rapidly that process takes place. Magma that starts at temperatures in excess of 1,000 degrees Celsius will cool rapidly in the relatively cold conditions of Earth's surface. This rapid cooling produces millions of tiny crystals of different minerals that can only be observed using a microscope.
In contrast, plutonic igneous rocks cool slowly under much hotter conditions, allowing some minerals to grow into relatively large crystals that can be readily distinguished by the naked eye. The same type of magma can produce either plutonic or volcanic rock, depending upon where it comes to rest.
Geologists can use the texture of an igneous rock, that is, the size of the crystals or minerals within the rock, to determine if it had a plutonic or volcanic origin. Visible grains indicate a plutonic igneous rock, but if you can't see any individual minerals, it must be a volcanic igneous rock.
For example, is this rock volcanic or plutonic? How about this one?
We can't see any individual crystals or mineral grains in the first rock, so we would classify it as volcanic. We can clearly see light and dark minerals in the other sample, so we would identify it as plutonic. How about these examples?
We can differentiate volcanic and plutonic rocks on the basis of their texture, but if we want to classify igneous rocks further, we have to divide them up by composition. We'll use the silica content of the igneous rocks to divide them into three groups. Fortunately, we don't have to do any fancy chemical analysis to determine composition, as the color of the igneous rock serves as a proxy for its silica content. Light-colored rocks are mainly composed of silica-rich minerals. In contrast, dark-colored rocks are made of silica-poor minerals.
We use the terms felsic, mafic, and intermediate to label igneous rocks with high, low, or medium silica contents. Felsic igneous rocks are silica-rich and are dominated by light-colored minerals. Mafic rocks are darker, and intermediate igneous rocks contain roughly equal measures of light and dark minerals. The chemical composition of these rocks ranges from about half silica for the mafic rocks to more than 2/3 silica in the felsic rocks.
Let's try classifying a few igneous rocks by composition. What about these examples? Can you identify the felsic, mafic, and intermediate varieties? Here are the answers.
Now that we know how to identify the texture and composition of igneous rocks, we are ready to learn how to apply this information and match it with the names of some common igneous rocks. We can separate igneous rocks into volcanic and plutonic varieties on the basis of texture, and there is a felsic, mafic, and intermediate example of each, giving us 6 possible rock names.
Felsic volcanic plutonic rocks are known as rhyolite and granite respectively. Their intermediate equivalents are andesite and diorite, and the darker mafic volcanic igneous rock is basalt, and the plutonic version is gabbro. Try creating this table on your own as a useful way of remembering the classification scheme. Now, let's see if you can apply this newfound knowledge to identify some igneous rock samples.
We see visible light-colored grains, so this must be a plutonic felsic igneous rock, and that would be granite. You are on your own now for the rest. Good luck.
So, to summarize, we can use the texture of igneous rocks to tell us something about where they formed relative to Earth's surface, and their color to indicate their chemical composition. In a future lesson, we'll discuss how composition is linked to the plate tectonic setting where the magma originally formed. On the basis of texture and color, geologists can classify igneous rocks and use this information to decipher the geologic history of the region where the rocks were found.
We had 3 learning objectives for this lesson. How confident are you that you could readily complete these tasks?